Hello everyone. Today is the last lecture of this week. What we were discussing in the last class is we just introduced what is kinematic indeterminacy. We demonstrated kinematic indeterminacy through some example on truss and also one example on simply supported beam. What we will be doing today is we will show you some more example of kinematic to determine kinematic indeterminacy. And then compare and then see what are the steps of force method and compare them with the displacement method, and through that comparison we introduce what is displacement based method. Okay. Now let us see some example. Now first example is, you see, this is a fixed beam. Consider a fixed beam. A fixed beam means both ends are fixed, and if the beam is fixed and it may undergo deformation like this for any arbitrary loading on this, any arbitrary loading like this. Okay. Now at this point delta is suppose this is A, this is B. So at this point delta H is equal to 0, horizontal delta H is equal to 0, delta V is equal to 0, and theta A is equal to 0. Similarly, delta H is equal to 0 here, delta V vertical displacement 0, and theta B is equal to 0. So in this, at this joint, all the degree, there is the degrees of freedom is 0. At this joint, degrees of freedom is 0, and the kinematic indeterminacy is the total degrees of freedom at various joints. So in this case, the total kinematic indeterminacy Nk will be 0. So it is kinematically indeterminate structure. Kinematic indeterminacy of this joint is 0. Of this structure is 0. Now take one more example. Same one end is fixed, and suppose another end is roller. Okay, it is propped cantilever beam, and if we deflects, then it may deflect like this under similar kind of. It may deflect like this. As I said, it is good to sense the deflection of a structure by looking at the boundary conditions and the applied load. Okay, so this is A, B. What is the degrees of freedom here? It is fixed support. So degrees of freedom is 0 here. Degrees of freedom is 0 here. All horizontal motion, vertical motion, and rotation, they all are restricted. Now in this case, delta H, delta V is 0. Delta V is 0. There is no vertical movement. Delta V is 0. And but delta H is allowed. Delta H is allowed, and theta B is allowed. Theta B is allowed. Okay. So here degrees of freedom is 0. Here degrees of freedom is 2. Okay. So total degrees of freedom is Nk is equal to 2. Now here is important point. Now if we assume that the axial rigidity of this beam is very high, there is no axial deformation, then delta H is also 0. Okay. So because delta H will cause axial change in length of AB, but if we assume that there is no change in length, there is no axial deformation, so delta H is equal to 0. If delta H is equal to 0, then how many degrees of freedom at joint B has? Joint B has just 1 degrees of freedom, which is theta B. So in that case, the Nk will be, Nk for this beam will be 1. Okay. So if we do not if we allow axial deformation, then kinematic indeterminacy of the problem of this beam is 2, and if we do not allow axial deformation, assume axial rigidity is very high, then kinematic indeterminacy is 1. We will see in the problem that many problems we assume, at least for the time being, will neglect the axial deformation. Okay. Now take one more example. This is a continuous beam. This is simply support here, then we have another roller support, then another roller support, and suppose this is A, this is B, this is C, and this is D. Okay. Now under action of, let's try to understand what would be the deflected shape of the beam. Under action of some load, deflected shape may be like this. Okay. it depends on the load, what kind of load you have and what is the value of the load. But when you draw the deflected, I am just drawing for some arbitrary loading case, this is, suppose this is the deflected shape. But when you draw the deflected shape, few things you need to understand, that displacement, the continuity of the slope and deflection is continuous at these joints, that you need to keep in mind. Okay. Suppose this is the deflected shape. Now, so end A is hinge support. Then what is the degrees of freedom here? What is allowed? There is no translation allowed. Only allowed is theta A. So theta A. Okay. Similarly, if you at see B translation is allowed and rotation is allowed, So what is allowed here is theta B is allowed, and delta B horizontal movement is allowed. And at C, then theta C is allowed, and then horizontal is allowed. Okay. And then what is at D? At D, theta D is allowed, then horizontal displacement of D is allowed, and also vertical displacement of V allowed, because at D there is no support at all. So in planar structure, at any point we have 3 degrees of freedom. So all 3 degrees of freedom the point D has. Now, so total how many degrees of freedom it has? 1, 2, 3, 4, 5, 6, 7, 8. So here total degrees of freedom is 8. Okay. In total degrees of freedom is 8, means Nk is equal to 8. Now, but this, when we say that the kinematic indeterminacy is 8, we have not made any assumption whether the axial deformation is allowed or not. But if we do not allow axial deformation, then what happen? This is not allowed. This horizontal motion is not allowed, because in this planar structure, if the point B moves here, then means there is a change in length in AB. If C moves here, then there is change in length in CB, or if D moves here, there is a change in length in AD. But the change in length, the axial deformation is not allowed. So delta C will also be 0, and delta horizontal, this is also 0. Then what is the degrees of freedom now? What is the kinematic indeterminacy now? Kinematic indeterminacy become 1, 2, 3, 4, 5. So total kinematic indeterminacy is 5 for this problem. Okay. So it is very important whether when you write the kinematic indeterminacy, it is very important to know or state whether you are actually allowing axial deformation or not. Okay. Now take one example of a frame problem. Suppose this is a frame, and this end is a fixed end. This is A, this is B, and this is C. Okay. Suppose at C we have a roller support. Okay. Then what happens? Probable deformation of the, let us draw the probable deformation of the structure. It may become something like this. Okay. May become something like this. Okay. For some loading condition. Okay. Now, at this point it is fixed support, there is the degrees of freedom is 0, rotation is not allowed, and any translation is not allowed. Okay. And what at point B? At point B we have theta B, and then we have delta HB, horizontal motion of delta H, and then delta VB at point B. So point B can rotate, point B can move in this direction, and point B can move in vertical direction. So if we just draw this point B can translate in this direction, point B can translate in this direction, and point B can rotate as well. Okay. Now what happens to C? The point C is, at point C we have theta C and we have delta CH. Okay. Because point C, at point C can move in this direction, point C can move in this direction, and point C can rotate in this direction. There is no vertical displacement at point C because it is roller support here. Then what is Nk? Then Nk becomes 1, 2, 3, 4, 5. nk become 5. Okay. Now, when we say nk is 5 for this case, we have not made any assumption that the axial deformation is allowed or axial deformation is not allowed. Now, if axial deformation is not allowed, if axial deformation neglected, then what happens? Now, let us see if the axial deformation of neglected, what happens to these degrees of freedom. Okay. Now, see what is the consequence of theta b? Theta b tells you how the point B rotates. Okay. And what is delta VB? Delta VB means how this point B moves in this direction. Okay. Now, you see if the point B moves in this direction, then what happens? Then the length of AB changes. The effect of this alone. When we are looking at each degrees of freedom, please see the effect of each degrees of freedom alone, and then see whether these degrees of freedom is allowed or not. Now, if we allow point B only to move in this direction, and this will cause change in length in AB, this will cause axial deformation in AB. Now, if the axial deformation is neglected, then this cannot be possible, isn't it? Okay. Now, so delta HB is possible. Now, look at point C. What is theta C? Theta is the rotation at point C. Rotation at point C is allowed. Now, see what is delta CH, what is the effect of delta CH? Effect of delta CH is point C moves in this direction, and what is the effect of HB is HB point move in this direction. Now, if delta this value and this value, and this value, they are different, means the amount by which point B moves in this direction and the amount by which point C moves in this direction, if they are different, then what happens? Then the length BC either they increase or they decrease. If point B moves more than point C, then the length of BC decreases, and if point C moves more than point B, the length of BC increases, isn't it? So, but increase or decrease in length is not allowed here, because we are neglecting the axial deformation. So, the member BC will not experience any axial deformation only when delta HB is equal to delta HB is equal to delta HC. So, horizontal displacement at B is equal to horizontal displacement at C. If this is ensured, then only there will be no axial deformation in BC. Okay. And suppose this is delta or this is delta. Okay. So, we can combine this and this, then how many degrees of freedom we have? We have theta B, rotation at B we have, then rotation at C we have, then we have delta HB, which is equal to delta HC is equal to delta. So, we have degrees of freedom, this is 1, this is 2, and this can be treated as 1 degrees of freedom, because if we know delta, then we know delta HB or delta HC. So, this is 3. So, in this case total NK is equal to 3. Okay. So, if we do not neglect the axial deformation for this same problem, the kinematic indeterminacy is 5, but if we neglect axial deformation, then kinematic indeterminacy for this problem will be 3. So, you can find out kinematic indeterminacy if you see any book, then there are different kinds of example given, different example on trusses, different example of beams with different support condition, and different example on frames with different support condition with internal hinge. and so you can apply the same concept to find out the kinematic indeterminacy. But when you find out the kinematic indeterminacy, you please you keep in mind whether you are allowing the axial deformation or not. If you do not allow axial deformation, the whatever possible movement at various joints may have all the possible movements we need to consider. But if you do not allow axial deformation, then the movements, the degrees of freedom which may cause axial deformation in various member, those degrees of freedom needs to be neglected. Okay, or now and then the kinematic indeterminacy needs to be determined. So, to get more in order to be more comfortable with determination of kinematic indeterminacy for various structure, I suggest you please go through the books and see some of the examples given in the book. Okay. Now, what we do quickly is let us introduce what is displacement measurement. That was our objective. You see, the entire concept of structural analysis, that at least for this course what we are studying, that is based on 3 pillars. Okay. And what are those 3 pillars? These 3 pillars are the entire structural analysis is based on 3 pillars, and these 3 pillars are one is equilibrium. What it says, the internal forces is equal to external forces, or the total forces in a particular direction or total moment about any point, they should be equal to 0. So, that is the equilibrium equation. Then the next pillar is the displacement compatibility, means the whatever if displacement if any structure, any force system satisfy the equilibrium condition, we say that this is this is statically admissible force system. So, equilibrium condition gives you the statically admissible forces. Okay. Now, displacement compatibility means displacement and various joints should be compatible to each other. If for instance, the slopes, whether it talks about the continuity of the slope, it talk about whether the displacement is allowed, whether rotation is allowed, all the problems, all the constraints that in a structure we may have, all these constraints should be satisfied properly. So, this is displacement compatibility, and if the displacements are compatible, then we say that the system that we have, that is kinematically admissible. So, a solution which satisfy equilibrium condition and which satisfy compatibility condition, that solution is the unique solution, that is the statically admissible as well as kinematically admissible. So, in order to get the unique solution for indeterminate structure, then we need both equilibrium and displacement compatibility. And then finally, we have the constitutive relation, which tells you how the forces are related to displacement or stresses are related to strain. So, we have the forces, we need to find out displacement, get the force displacement, apply substitute those forces in the force displacement relation, get the displacement. Or if we know the displacement, in order to get the force, you substitute the relation and then get the forces. So, whether the force displacement relation, whether we know force and determine the displacement, or we know displacement, determine the force, depending on that we either use the flexibility format or use the stiffness format. The flexibility and stiffness format we discussed in the last class. Okay. Now, if the structure is statically determinate, equilibrium condition is alone sufficient to give you the solution, but if it is not, then we need, along with equilibrium conditions, we need displacement compatibility, and in order to get the relation between force and displacement, we need constitutive relation as well. Now, how these 3 pillars are used, okay, in what order these 3 pillars are used, depending on that we have 2 methods. One is force based method and one is displacement method. But in all the methods, either force or displacement method, they are premise of all these, both the methods are these 3 pillars. Okay. Now, but how these 3 pillars, how these three ingredients are used, in which order they are used, depending on that we have 2 methods, force method and displacement method. Now, what I will do is we discuss the steps of force method, different steps of force method, We introduce the force method through an example, but that we are not going to do it for displacement method. We know the different steps for force method, and we will see what are the corresponding steps in displacement method. Okay. Okay. So, these are force method, which are also called flexibility method, displacement method, which are also called stiffness method, that we discussed in the last class. If you remember, in the force method, the first thing what we do is first thing we calculate the what is the static indeterminacy of the problem. Okay. And but in the stiffness method, what we do is what we find out what is the kinematic indeterminacy. We just discussed how to determine kinematic indeterminacy for different structures. Now, in force based method, then once we know the static indeterminacy, then we need to understand what are the redundant forces. When we say the forces, it includes force and moments both. So, identify the redundant forces, right. But in this case, in the displacement method, we need to identify what are the unknown displacements, and the number of those unknown displacements should be equal to the kinematic indeterminacy of the structure. So, in the force based method, we need to identify the forces, and in displacement based method, we need to identify the displacements. As name suggests, it is very obvious from the name. In the force method, force is essentially the unknown, and the displacement method is the displacement which are unknown. Okay. Now, then what we do in the force based method, we find then we solve the basic determinate structure which are subjected to load and the redundant forces. But what we do in displacement based method is restrain the above displacements, whatever displacement, unknown displacements we have, those displacements are needs to be restrained, and find the forces in the basic structure. Now, when we divide the structure in the force based method, we need to ensure that all those primary structure, the basic structures, are statically determinate, and in displacement method, when we divide the structure into small substructure, we need to ensure that all these small substructures are kinematically indeterminate. Okay, kinematically determinate, and then we find out the okay, and find the forces here. Okay. And now next step is, once we know the displacements, then the displacements are expressed in terms of redundant forces using the flexibility format, but in displacement method, we need to express the forces in terms of displacement in the stiffness format. Okay. And then in flexibility method, we write the compatibility equation and solve the compatibility equation, and finally in displacement based method, once we have this form, we solve those that form, means we solve the equilibrium equations for unknown displacements. And now some of the steps will not be clear, which is very obvious, but the reason I did not introduce through a problem, because we already have done that for force method. Here the objective is we know the steps for force method, what is the corresponding steps for displacement method. Okay. But those steps will be explained in detail when we actually derive when we actually formulate the displacement methods and apply to different kinds of problem. Here the objective has been to just tell you that in what sense those two methods are different, what are the recipe for all these methods, okay, of the entire week. That has been the purpose of the entire week. Now, the recipe is ready. What we need to do is we need to start the cooking, and that we will be doing from next week. Next week, what we do is next week we will start with force method. Next 2 weeks we will spend on force method, and then after that another 2-3 weeks on displacement method. In the force based method, we will discuss method of consistent deformation. Will first apply the method of consistent deformation for trusses, and then method of consistent deformation for beams and frames. And then once we have done that, and after that we'll derive the displacement methods and apply to different problems. Okay, then thank you. See you in the next week.